Hello everybody, welcome to the second part of metals and non-metals. In this part of the chapter, we would be focusing on the last part of the chapter, which is around the metallurgical process. Now, in the metallurgical process, students often get confused with all the terms that are associated because some of these terms can be very new and unique to some of you. So having said that, let's quickly learn to summarize this chapter as quickly as possible. Now, one thing that we need to understand is metallurgical process is required for you to be able to extract the pure form of metal from its ore in the most profitable and convenient manner. So the first thing that you'll have to do is find a place where the ore of the metal is available. For example, if you would want to make steel, you would want to go to a place that has steel. For example, Jharkhand or Tatanagar in India is found to have large deposits of iron. So people generally go there to extract iron from their ores and then make pure iron out of it. Now, how does the entire metallurgical process work? It first starts with you identifying what metal you would like to extract. You would want to go there, dig the earth, which is called mining, and then perform a set of tasks before you're able to get the pure form of the metal. Having said this, let us look at what the end-to-end metallurgical process is going to look like. The first step in metallurgical process is called mining, where you dig the earth and you extract the ore or the mineral of your choice. Now, generally at the end of the mining process, there are two things you're going to get. One thing is the ore, and the other thing that you're going to get with it are the earthy impurities. For example, when you're digging, you can get some mud, you can get some stones and all of that. Those mud and stones are called as gangue, or sometimes also referred to as matrix. So at the end of the mining process, you're going to get ore and you're going to get a lot of gangue. Now generally, gangue will be in a much larger quantity compared to the ore. Your job is to remove the gangue as quickly as possible. Now, one of the first steps that you're going to do to remove these impurities or gangue as quickly as possible is called as pulverization. Now, pulverization is the process in which you would be able to remove most of the gangue by first converting it into fine powder. So, pulverization is the process in which you send the ore and gangue through large crushing machines. And when you send them through these large crushing machines, you will be able to get powdered ore and gangue. There are two benefits of this. One, you will be able to handle it better instead of using big boulders which are very difficult for you to transport and all of that. If you convert it to fine powder, it's just so much more easier for you to remove the gangue. And the second thing is you could use all the techniques that we're going to discuss after this, and you can use one of these techniques suitable to remove the gangue as quickly as possible. Once you pulverize it or convert it into powder, the next step is to remove the gangue out. Now, the step that we're going to call now is called as enrichment of ore, or sometimes also referred to as concentration of the ore. In certain books, you may also see the word ore dressing. So basically what you're doing is trying to get rid of the gangue particles. Now, there are four methods that we generally use for this. There are many more, but I'll tell you the most common ones. First one is called as levication or gravity separation. The second one is called as froth flotation. The third one is called as magnetic separation. And the fourth one is called as the chemical method. Now in NCERT, he's not really spoken much about these methods, but it's important for you to know because in case some question is asked around it, you should be able to answer it. Now levication is generally used when the ore is heavier than the gangue. So the gangue is the lighter particle. Froth flotation is mostly used for sulfide ores. Magnetic separation is used for magnetic ores. And chemical method is mostly used for bauxite ores, which is an ore of aluminium. Okay, so let us briefly discuss what we do in each case. For levication, what we do is we take an inclined surface, we make small gaps in them called grooves, and then we just wash the pulverized ore and gangue down the slope. All the heavy particles get accumulated in these gaps, and all the lighter particles get washed down. You keep repeating it until you'll be in a position to separate both the ore and gangue. In froth flotation, you mostly use it for sulfide ores, and remember they will ask you mostly around zinc blend, which is ZNS. Sometimes they could also ask you around copper glance, which is CO2S, or sometimes even around FeS2, which is called as iron pyrites. So they could use any of this and ask you questions. So if they ever ask you what method you use, since all three of them are sulfide, you would use the word froth flotation for them. Magnetic separation is mostly used for magnetic ores like magnetite and all of that. They're mostly made of iron. Chemical process is used predominantly for bauxite, and the chemical that you use here is sodium hydroxide. The reason why you use sodium hydroxide is because bauxite contains aluminium, which is amphoteric. And since it is amphoteric, it is going to dissolve in sodium hydroxide. And in that step itself, the gangue particles can get separated out. So aluminium will go away with sodium hydroxide, leaving all the gangue particles behind. Having said that, once you finish the entire process of enrichment, the next process that you do is you do a check. You check if your ore is in oxide form or non-oxide form. Is it in oxide form or non-oxide form? Now, if it is in oxide form, you can skip the fourth step. If it is in non-oxide form, you need to then do either of these two things. One is called roasting and the other is called calcination. Roasting is used again for sulfide ores, and calcination is mostly used for carbonate ores. Now, roasting is where you're heating the ore. Now at this point you've removed most of the gangue, right? Because concentration took care of most of the gangue. So what you're going to use here as a keyword is concentrated ores. So the definition is heating a concentrated ore in excess air or oxygen is called as roasting. And the ores that predominantly undergo roasting are sulfide ores. For example, let's take zinc sulfide. Now since it's a sulfide ore, it has already undergone froth flotation. Now that we have zinc sulfide, I'm going to add oxygen and we shall heat it. When you heat it, it gets converted to zinc oxide and releases out volatile gases such as sulfur dioxide, which readily escape. Your job at the end of this fourth step is to convert everything to oxide form. Now a common question we get asked is, why should everything be in oxide form? It should be in oxide form for a simple reason that reduction becomes easier. Because all you now have to do is remove the oxygen out and you will be able to get the metal out of it. Okay? Now, apart from this, you also have another important ore of sulfide called as galena, PbS, spelled as Galena. This also undergoes roasting when you heat it in the presence of oxygen to give you PbO plus SO2. Now please remember, the keyword that you need to use here is excess air or oxygen. You have to heat it with excess air or oxygen. Let's look at what calcination is. Calcination is where you're heating the concentrated ore in very little oxygen or no oxygen itself. So this generally takes place in a closed container because you do not want any oxygen to come in contact. You take a carbonate ore, like calcium carbonate. When you heat it, you get calcium oxide plus carbon dioxide. So in this reaction, do not add oxygen, right? So you get calcium oxide and carbon dioxide. At the end of it, you have oxide here, you have oxide here as well. Now that everything is in oxide form, the next step is obviously to remove that oxygen. Because you all have that oxygen here, you have to remove that oxygen from the ore. How do you remove oxygen? By a process called as reduction. All of us know reduction means removal of oxygen. So that is going to be the next step. So in the fifth step, it is called as reduction. In the reduction process, you take any ore. It's oxide, everything is on oxide form now. You can take ZNO. I'll give you more examples as we go ahead. Your job is to remove this oxygen. The best way to remove oxygen is by using carbon as the reducing agent. Now, when you use carbon as the reducing agent and when you heat it, carbon and oxygen combine together to give you carbon monoxide, leaving behind zinc. Now, if you notice, zinc oxide is losing oxygen to become zinc. So, zinc oxide is getting reduced. Carbon is getting oxidized. So this is a classic example of a single displacement reaction or even a redox reaction. Now you can also do other methods as well. For example, when you look at aluminium. Now aluminium's ore is called bauxite. Now bauxite is actually Al2O3.2H2O, but I've just taken Al2O3 for now. This Al2O3, the problem is, this bond that you see here between aluminium and oxygen is very, very strong, because aluminium is a strong metal. So by heating it in the presence of a reducing agent like the way we did for zinc may not be good enough, because it may not help in breaking that bond. And even if the bond breaks, the quality and quantity of aluminium that you're going to get at the end of it is going to be very poor. So in situations like this, if reducing agent doesn't work, you use a process called as electrolysis. And through the process of electrolysis, you will be able to convert aluminium oxide to aluminium. Now, the detailed process is not required for you to know for your 10th standard board exams, but you need to know that the first most reactive metals, which is potassium, sodium, calcium, magnesium and aluminium, all should undergo electrolysis process to reduce their metallic oxide to metal form. Whereas metals that are slightly below, it could be zinc, it could be iron, it could be lead, it could be copper, all of these undergo reduction technique by using a reducing agent. And in most cases, the reducing agent used would be carbon. In certain cases, for copper example, you could use Cu2S as the reducing agent, and I'll show you how that reaction works as well. But predominantly, you're going to use carbon as the reducing agent. Now, if carbon is used as a reducing agent, there's a special name given to it called smelting. So if anybody ever asks you to define smelting, smelting is the process of reducing, please use the keywords, reducing metallic oxides to metals by using carbon as the reducing agent. So sometimes this is also called as smelting of zinc oxide. Alright, so smelting of zinc oxide means you're adding carbon to zinc oxide. Clear? Now, what do we do with metals such as mercuric oxide? Now, mercuric oxide, if you want to extract mercury out of it, the bond between mercury and oxygen that you see here is very weak. Your job is to just break that bond because you need to get rid of oxygen. So the best way to do that is just heating it. When you heat it, HgO becomes Hg, liberating oxygen gas. HgO is orange in color, and towards the end of it, you will be able to get or see silvery globule pattern of mercury. Simple. Alright. Now that we have understood all the reduction processes, we must also understand that if you go back to this reaction, the zinc that you have obtained here is not really pure zinc. It might still have a few gangue particles in it. So the last step is to make sure that you get rid of the final gangue particles, and those final gangue particles can be removed by a process called as electro-refining or just refining. But before we go there, there is one more important question that they will ask you in your exam, and this is around reducing Fe2O3. Now Fe2O3 is also called as hematite. Hematite is a very common ore of iron. I'll give you the list at the end of it, the ones that you need to know. Whenever hematite has to be reduced, you could use carbon, but sometimes they also use aluminium as the reducing agent. Always remember, metals can act as good reducing agents. And since aluminium lies above iron in the reactivity series, aluminium can act as a better reducing agent than iron. So what aluminium is going to do now is, when you heat it, aluminium will combine with oxygen to give you aluminium oxide. And in the process, this iron oxide that is there gets converted to iron. Now generally what happens is, if you look at the industrial application of it, if I have a little funnel like this, and if I place a combination of Fe2O3 and Al, and using a magnesium ribbon, if I just light this, then towards the end of the reaction, I'm going to get Fe in liquid state. So Fe is going to trickle down here. So you can use your molten Fe for something. And you know what they use this for? They use this to repair any cracks in bridges or railway tracks. So that iron will fall off here, it will solidify here, and you will be able to seal that crack out very well. This process is called as the Thermite process, sometimes also called as the aluminothermite process, and this mixture that you see here is called as the Thermite mix. Very common question in the exam. Now that you've obtained these metals, let us look at the last step in which you can electro-refine them or just refine them. Now, the most common metal that we refine is copper. So I'll tell you how that works. Take a container which is called as the electrolytic cell, and into that you add a salt of copper. The most common salt of copper you add is copper sulfate. Into this you introduce two electrodes. This is the first electrode and this is the second electrode. Now the first electrode is made up of impure copper. Now impure copper was what you obtained from the previous step, and this cathode that you see is called pure copper. What you do next is you convert this to a battery. You can add a switch, etc. of your choice. Keep some potential difference of V. Now what you'll have to do is you'll have to add a little bit of acid to CuSO4 to make it a better conductor. So let's add few drops of H2SO4, and this becomes acidified copper sulfate. Alright, now that you have understood what the electrolyte is, this electrode that is connected to the positive terminal is called as the anode. This which is connected to the negative terminal is called as the cathode. Now let's see what happens. The moment you start passing electricity, the first thing that's going to happen is this CuSO4 that is there in solution will dissociate to give you Cu2 plus ions plus SO4 2 minus ions. These Cu2 plus ions, being positively charged, will get attracted to the negative terminal and they start moving in this direction. When they start moving in this direction, they go to the cathode. So let's see what happens at the cathode. These Cu2 plus ions will gain 2 electrons to become Cu solid. Now the best way to remember it is, if I have a plus 2 here, put plus 2 electrons next to it. If I had a minus 1, I would have put minus 1 electron. If I had plus 3, I would have written plus 3 electrons. So whatever I see here, you put the same thing here with the same sign as well. That's the easiest way to remember. Now that copper starts going to the cathode, this copper ions start getting deposited as copper metal. Now there's a difference. Cu without any charge is called copper metal. Cu2 plus is called as copper ion. So ideally what is happening is copper gets reduced to give you copper ion gets reduced to give you copper metal. So at the cathode, you will start seeing a lot of copper get deposited. So the size of the cathode starts increasing. Now we have understood what happens here. So the size of the cathode keeps increasing because copper goes in, gets deposited. So your pure copper that was there is going to have more and more pure copper come and deposit on top of it. So the size slowly begins to increase. Now let's see what happens at the anode. At the anode, this SO4 2 minus ion starts going towards the anode. Simultaneously at the anode, you know the anode consists of impure copper. Out of that impure copper, some of the good copper will lose 2 electrons to become Cu2 plus. So this electrode that you see will start generating Cu2 plus, and those Cu2 plus ions starts getting into the solution. The moment it gets into the solution, it encounters the SO4 2 minus that is there all around here. You know, it's like this tank of fish and someone is waiting to pour food, right? You see how all the fish come together to eat the food. So as soon as Cu2 plus comes in, all the SO4 2 minus try to grab it. And when this Cu2 plus ions is taken by SO4 2 minus, you get CuSO4. So ideally now what is happening is, one Cu2 plus ion comes from the electrode, combines with SO4 2 minus to form CuSO4. This CuSO4 falls back into the solution. So we lost one CuSO4 here, so one new CuSO4 comes from the anode. So the observation you're going to make in this reaction is that the color of copper sulfate remains blue throughout the reaction. That is because for every one copper 2 plus ion that went to the cathode, one new copper 2 plus ion gets generated at the anode. Now, since copper is getting deposited at the cathode, the size of the cathode is going to increase. However, since copper 2 plus ions are being produced at the anode, the size of the anode will start shrinking. So over a period of time, you will notice that the size of the anode becomes smaller and smaller and smaller. After all the Cu2 plus ions from here have come out, all the remaining things that are not Cu2 plus, which are also called impurities, will all crumble and they will all fall down and they will sit below, and that is called as anode mantle. So at the end of the reaction, you will see no anode left because all the good copper has got deposited onto the cathode. All the impurities have crumbled and fallen down. Now here, what type of question can you expect? You can expect this important question. What are the products found at the anode and cathode respectively? At the cathode, you are going to get pure copper metal, and at the anode, you are going to get Cu2 plus ions. Don't forget this. So the products formed are at the anode, the product formed is Cu2 plus ions, and at the cathode, the product formed is Cu metal. I hope there's absolutely no confusion around this. Alright, with this we will be able to extract the purest form of metal starting from the first process. So to summarize, you can all do this with me, you can pause the video if you want in between. We will be making a flowchart just to summarize the entire end-to-end metallurgical process. We started with the first step, which was mining. At the end of mining, we got boulders of ore and gangue. After this process, we had to powder everything, so it underwent a process called pulverization, where we were able to get pulverized ore plus gangue. After this, we were trying to get rid of the gangue particles, so we ran it through an enrichment process or concentration process. Concentration process had four ways of doing it. One was levitation method, one was froth flotation, one was magnetic separation, and one was chemical method. Levitation method is generally used for heavy ores such as silver, gold, platinum. Froth flotation is mostly used for sulfide ores. Magnetic separation used for magnetic ores. Chemical process is used for Al2O3.2H2O, which is bauxite. The moment you finish the concentration process, what you mostly get is ore in pulverized state. So you just get pretty much just powdered ore, but some amount of gangue particles might still be there. The moment you get that, you do a check. What check do we do? Is ore an oxide? If ore is an oxide, then skip the process. If ore is not an oxide, convert it to oxide. Why do we have to convert it to oxide? So that reduction becomes easy in the next step. Converting to oxide is either in the form of roasting or in the form of calcination. Roasting is where you heat it with oxygen. Calcination is where you don't require oxygen. The best way to remember it is roasting is like peanuts. If you have seen people roast peanuts, it's always done in an open kadai so that there's more oxygen that can come there. Calcination is in a closed container, so the best way to remember this is popcorn, because it's in a closed container. At the end of this, what we get is something called as an oxide ore, and finally we have to run it through a reduction process. Now reduction can be of three types. One is called as electrolytic reduction, which is generally used for aluminium, magnesium, calcium, sodium, potassium. You could also use smelting, where you use carbon as the reducing agent. This is mostly used for zinc, copper, iron, lead. Then you could also use thermal or heat for very weak metals such as silver or mercury, silver. Okay, after all this is done, the last step which I'm going to write here is where you reduce it. Where you refine it. In the process of refining, you will be able to get the pure form of metal, and this will conclude the entire end-to-end metallurgical process. Now, what type of questions could you mostly get asked here? They might ask you to name a few important ores of certain metals, which I'll summarize in the next slide. Or they could ask you a little bit of things here and there. Sometimes they'll ask you the role of roasting or the role of calcination, or they could ask you the definition of smelting. They could ask you what aluminothermic process is. All those things can be asked. They could ask you for industrial applications. They could ask you what anode mud is. They could give you a diagram and they could ask you to describe the diagram or ask you questions based on it, etc. Alright? What I would suggest you do at this point is just pause the video for 2 minutes and try to make the summary on your own. And after this, I will be moving to a new slide and I'll be listing down a few important ores so that we can conclude the 2 parts of this chapter. Now let us look at some of the most important ores. First, Al2O3.2H2O is the ore of aluminium, and this is called as bauxite. Then we have Cu2S, which is the ore of copper, which is called as copper glans. PbS is called galena. Then ZnS is called zinc blende. Then HgS, which is an ore of mercury, is called cinnabar. NaCl is a very common ore of sodium, which is called common salt or sodium chloride. Alright, I think if you can remember some of these for these metals, it's good. I'll also list down 2 important ores of iron that is necessary for you to know. Fe2O3 is called hematite, and Fe3O4 is called magnetite. You also have iron pyrites and copper pyrites and all of that, but I think this should be good enough for you to remember all the ores of this chapter. I hope you enjoyed the video, and I hope this video helps you become thorough with the subject so that you could score good marks in your exam. Best of luck as you write your exams, and do well. Thank you.